Hi, my good friends. My name is Tete Kepsi Richard, and welcome to my online tutorials. Our discussion on discrete mathematics and relation for that matter will be on partially ordered set, or POSET for short. So before the video ends, we'll look at when a set that a relation is defined on, when that set is said to be a POSET. This will be a very interesting engagement, so please come along. So we say if a relation R is defined on a set A, then the set A is said to be a POSET if the relation R is partially ordered. So what does this mean? It simply means that when a relation is defined on a particular set, that set will be called a POSET if the relation defined on it is a partially ordered set. That means the set is called a partially ordered set if the relation is partially ordered. And when do we say a relation is partially ordered? A relation is said to be partially ordered if it is reflexive, antisymmetric, and transitive. Thus, a relation is said to be partially ordered if it satisfies three conditions. Thus, it should be reflexive, it should be antisymmetric, then it should be transitive. So this simply means that when any set is given to you for you to determine whether the set is a partially ordered set or a POSET, find out the relation defined on that set. Find out whether that relation is partially ordered. Thus, the relation is reflexive, antisymmetric, and transitive. If the relation satisfies these three conditions, then it is partially ordered. Then we can say that the set on which the relation is defined on is a partially ordered set, or POSET for short. I hope you get that. So now we take some sample problems and find out whether the set on which a relation is defined on is a POSET. So let's look at our first example. They say a relation R is defined on a set A equal to 1, 2, 3, 4 as R with members 1, 1, 1, 2, 1, 3, 1, 4, 2, 2, 2, 4, 3, 3, and 4, 4. We should determine whether or not the set A is a POSET. So how do we do this? Remember we said a set is said to be a POSET if the relation defined on it is partially ordered. I hope you know that. Then we said that a relation is partially ordered if it is 1. reflexive, 2. antisymmetric, and 3. transitive. So what are we going to do? We'll take this relation and find out whether the relation satisfies all these three properties. That's reflexive property, antisymmetric property, and transitive property. If the relation satisfies all these three properties, then the set on which the relation is defined on can be referred to as a POSET. So please do well to check out my videos on how to determine if a relation is reflexive, antisymmetric, and transitive on YouTube. So now we test the relation and see if the relation satisfies all these three properties. So for reflexive property, we say that a relation is reflexive if A, is a member of the relation for all A is a member of the set A. That means all the elements in the set A must have a self-loop or must relate themselves in the relation. If they all relate themselves in the relation, then we can say that the relation is reflexive. So let's check. Do we have 1, 1? Yes. So we can say 1 relate 1. Do we have 2, 2? Yes, 2, 2 is here. Then we can say 2 relate 2. Do you have 3, 3? Yes, we have 3, 3. Then we can say 3 also relate 3. Do we have 4, 4? We have 4, 4. So 4 relate 4. Then therefore, the relation is reflexive. So our relation satisfies the first condition. Now let's look at the second condition. We said that's antisymmetric. A relation is said to be antisymmetric. Okay? If A relate B is a member of the relation and B relate A is a member of the relation, then A must be equal to B. So we say that. So that means that we flip all the members of the relation. If the resultant flipping is a member of the relation, then that means that the first element is equal to the second. If not, and it is a member, then it is to be antisymmetric. So let's check. Look at it. 1, 1, 1. When we flip 1, 1, we still get 1, 1. 1, 1 is a member of this relation, but 1 is equal to 1, so it satisfies the condition. Then we don't have a problem. Now let's flip 1, 2. When we flip 1, 2, we get 2, 1. But 2, 1 is not a member of the relation. We are good to go because 1 is not equal to 2. When we flip 1, 3, we get 3, 1. 3, 1 is not a member of the relation. Then we are good to go because 1 is not equal to 3. When we flip 1, 4, we get 4, 1. 4, 1 is not a member. So when we flip 2, 2, we still get 2, 2. But 2, 2 is a member of the relation. But let's check. 2 is equal to 2. Then we are good to go. Let's flip 2, 4. When we flip 2, 4, we get 4, 2. 4, 2 is not a member. We are good to go. When we flip 3, 3, we'll get 3, 3 again. 3, 3 is a member, but 3 is equal to 3. We don't have problem. When we flip 4, 4, we still get 4, 4. 4, 4 is a member. However, 4 is equal to 4. Then we can conclude that the relation is anti-symmetric because it satisfies the condition of anti-symmetric property. Now the next one is the transitive. The transitive, I prefer using a table so that I can get the full glance of the problem so that I will not eliminate any of them. So I will draw a table and I will use it to check the transitive property. So we realize that our relation satisfies the reflexive property and the anti-symmetric property. The next one is the transitive property. We have to find it. So we say relation is transitive if A relate B is a member of the relation and B relate C is also a member of the relation. Then A relate C must also be a member of the relation. So that's it. So I usually do this. So I'll have my first one, A relate B, by listing all the members of the relation here. Then my next step, I'll get the other pair BC. So if I reach here with 1, 1, I'll list the other pair where the 1 starts here. So we have 1, 1, then we have 1, 2, then 1, 3, and 1, 4. So when I come here, I'll list the other pair that 2 begins it. So the other pair that 2 begins, see we have 2, 2, so 2, 2, then 2, 4. Then the other pair that 3 begins, the other pair that 3 begins, we have 3, 3. Then the other pair that 4 begins, look at that, we have 4, 4. When we come here, the other pair that 2 begins it, that's 2, 2, then 2, 4. Then here, the other pair that 4 begins, we have 4, 4. Then here, the other pair that 3 begins, we have 3, 3. Then here, the other pair that 4 begins, we have 4, 4. I hope you get that. So having gotten the BC, I need my AC. I call this the decision maker. So what I'm going to do is I'll take the first ordered pair here and the second ordered pair here. That becomes C, AC. So AC, the first here and the second here. So this one I will pick 1, 1, so 1. I'll have 1, 1, then 1, 2, 1, 2. I'll have 1, 3, then 1, 4. So 1, 3, and 1, 4. When I come here, I'll pick here 1, 2, so 1, 2, then 1, 4. So I have 1, 4. When I come here, I'll pick 1, 3, so I'll get my 1, 3. Here, I'll get my 1, 4, so 1, 4. Here, 2, 2, and 2, 4. So 2, 2, 2, 4. Then here 2, 4, so I have 2, 4. Here 3, 3, I have my 3, 3. Then here 4, 4, I have 4, 4. So the next thing is that we check whether all these ordered pairs here are members of the relation R. They are members of the relation R. So if you check, all the ordered pairs here are members of the relation R. If that's the case, then we can say the relation R is transitive. So since the relation is reflexive, antisymmetric, and transitive, then it is partially ordered. So we can say the relation is partially ordered. As far as the relation is partially ordered, then the set A equal to 1, 2, 3, 4 is a POSET. I hope you get that. So as far as our relation is partially ordered, then the set on which the relation is defined on is a partially ordered set. I hope you get that. We'll solve another example on this so that you get the concept. So before we solve our second example, please remember to subscribe to my YouTube channel, like and comment. It is the only way you can help me promote my YouTube channel so that I can record more mathematical content for you. So the second question is a relation R is defined on a set S equal to 1, 2, 3, 4 as R equal to the members 1, 1, 1, 2, 2, 1, 2, 2, 3, 4, 4, 1, and 4, 4. Determine whether or not the set S is a POSET. So what are we going to do? So we said that a set is said to be a POSET if the relation defined on the set is partially ordered. And a relation is partially ordered if it satisfies three properties: that it is reflexive, it's antisymmetric, and it is transitive. So what we are going to find out is that we determine whether this relation R is a partially ordered relation. If it is partially ordered, then the set S is also a POSET because the relation is defined on that set. So the first one, we'll find out whether the relation is reflexive. So we say a relation is reflexive if A, A is a member of the relation for all A is a member of the set S. So what are we going to do? We'll find out whether that all the members of the relation have a self-loops or they relate themselves. All the members of this set relate themselves in the relation. If they relate, then the set is the relation is said to be reflexive. So we find out whether we have 1, 1. Yes, 1 relate 1. Do we have 2, 2? Yes. Look at it. So 2 relate 2. Do we have 3, 3? No. So we said 3 does not relate 3. Do we have 4, 4? Yes. So 4 relate 4. However, because 3 elements relate themselves, but 1 does not, it disqualifies the relation for being reflexive. So we say the relation is not reflexive. So since the relation is not reflexive, it's even an enough reason to disqualify the relation for being partially ordered. But for academics, let's try to find the other properties. So we go to the antisymmetric. We say a relation is antisymmetric if A relate B is a member of the relation and B relate A is also a member of the relation. Then A must be equal to what? B. If A is not equal to B, then it is not antisymmetric. So let's find out. So we'll flip all the members of this relation. When we flip it and it is a member, it must be equal. If it is not a member and it is, when we flip and it is a member and it is not equal, then it ceases to be antisymmetric. So let's flip the first one. See, on flip 1, 1, we still get 1, 1. 1, 1 is a member of the relation. However, 1 is equal to 1. It satisfies the condition. On flip 1, 2, we'll get 2, 1. See, 2, 1 is a member of the relation, but 2 is not equal to 1. So that disqualifies the relation for being antisymmetric. So how do we say that? We say that 1 relate 2 and what? And 2 relate 1. But 2 is not equal to 1, or 1 is not equal to 2. Therefore, the relation is not antisymmetric. I hope you get that. So now the third property is to find out whether it is transitive. So for the third property, which is transitive, we say a relation is said to be transitive if A, B is a member of the relation and B, C is also a member of the relation. Then A, C must also be a member of the relation. Other than that, then it ceases to be transitive. So let's find out. So I usually use a table. I'll list all the members of the relation here as AB. Then the next step, I'll get my BC. In this case, I'll find out the relation, the ordered pair that 1 begins it. So we have 1, 1. 1 is, another one is there, so we have 1, 2. So when I come here, I'll list the ordered pair that 2 begins. So I'll have 2, 1, then 2, 2. Then when I come here, I'll list the ordered pair that 1 begins again, 1, 1, then 1, 2. Then here the ordered pair that 2 begins, 2, 1, then 2, 2. Here the ordered pair that 4 begins. See, we have 4, 1 and 4, 4. So 4, 1, then 4, 4. Then here the ordered pair that 1 begins, that's 1, 1 and 1, 2. Then the ordered pair that 4 begins, 4, 1, then 4, 4. Then I'll come to the decision maker, that's A relates C. In that case, I'll pick the first element here and the second element here in the ordered pair. So here 1, 1, I'll have 1, 1. Then 1, 2, I'll have 1, 2. When I come here, I'll have 1, 1, so 1, 1. I'll have 1, 2, 1, 2. Here I'll have 2, 1, 2, 1. Then 2, 2, 2, 2. Here I'll have 2, 1, so 2, 1. Then 2, 2, 2, 2. Then here I'll have 3, 1, so 3, 1. Then I'll have 3, 4, 3, 4. Then here I'll have 4, 1, 4, 1. Then I'll have 4, 2, 4, 2. Then I'll have 4, 1 again, 4, 1, then 4, 4. So I'll find out whether all the members here, all the other pairs here are members of the relation R. If they are members, then the relation is transitive. So if you find out all the elements, all the other pairs here are in the relation R, then we can say the relation is transitive. So what happens? You can realize that our relation, the relation R is transitive, but it is not reflexive and what? And antisymmetric. So since it satisfies only one condition, see, if only one of the conditions is not satisfied, it is an enough reason to disqualify it from being partially ordered. So we can say that the relation is not partially ordered. So since it is not partially ordered, then the set S is not a what? Is not a POSET. I hope you get that. This is very simple. So you just find out whether the relation satisfies the three properties. If it satisfies the three properties, then the set on which it is defined on is a POSET. If it doesn't satisfy, then the set on which it is defined on is not a POSET. So our third example says that we should show whether or not the divisibility relation that is partially ordered on the set of positive integers. So this one, a set is given, but the relation is not given. It simply means we need to find that relation. So the relation will be equal to A comma B, be a member of the relation, where A divides B, and A and B are positive integers. I hope you get that. So this is the relation. We need to find out whether the relation is partially ordered. So we say a relation is partially ordered if it is what? Reflexive, antisymmetric, and transitive. I hope you get that. So the first one, we need to find out whether our relation here satisfies all the three properties. If it do, then we can say it is partially ordered. So the first one, for reflexive, we say A comma B, A comma A must be a member of the relation where A is a positive integer. So it means that one will take a positive integer and it divide itself. So if A divides A, okay, when A divides A, we'll get 1, right? One will take any two positive integers and it divides each other. The result is 1. 2 divided by 2 is 1. 3 divided by 3 is 1. So we can say this is a positive integer. So the relation is reflexive. I hope you get that. So it satisfies the first condition. We check the antisymmetric. So we say a relation is antisymmetric. So for antisymmetric, A comma B is a member of the relation and B comma A is also a member of the relation. it implies that A is equal to B. So that's what we need to find out for the antisymmetric. So when we take two positive integers, if A divides B, the result will be a positive integer. So when we take two numbers and they divide each other, it will be a positive. When we alternate it and they divide each other again, it is a positive integer. So we can therefore conclude that A is therefore equal to B. So our relation, the relation is antisymmetric. I hope you get that. The next one is transitive. So for transitive, we said that if A, B is a member of the relation, and B, C is also a member of the relation, then A, C must also be the member of the relation. So what does that mean? It means that if A divides B, it's a positive integer, okay? And B divides C is also a positive integer. Then we can therefore conclude that if A divides C is also a positive integer, which is very true. Then the relation is transitive. So since the divisibility relation is reflexive, antisymmetric, and transitive, then it is a partially ordered. So since it is a partial, then we say that any set it is defined on, that set will be a POSET. We'll end it here today. Please remember to subscribe to my YouTube channel before you sign out. Like, comment on my video, share. It is the only way you can help promote my YouTube channel so that I can record more mathematical content with you. Until we meet again, my name is Kepsi.